Okay, now let's take a look at Riverside Secondary School paper 2 here. Okay, let's take a look at question 1. So we have the following oxides to look at. Okay, so each oxide can be used once, more than once, or not at all here. So when we are looking at the first one, giant molecular structure. So when we are looking at giant molecular structure, remember there is only 3 that you need to know. They are your diamond, graphite, and last one, which is your silicon dioxide, your SiO2. Okay, so therefore for part A will be silicon dioxide. Now, which oxides react with both acids and alkali? So when it reacts with both, we are talking about your amphoteric oxide. So for your level, you only need to know 3 amphoteric oxide, which is Z, A, and L. Zinc oxide, aluminium oxide, as well as your lead-2 oxide. So therefore, based on options that are given to us, it will be zinc oxide. Which one reacts with water to form a strong acid? Okay, so in order for us to, when it reacts with water, to form a strong acid, it means that this oxide has to be an acidic oxide. Okay, acidic oxide dissolves inside water to give us an acidic solution. So when we are looking at acidic oxide, we are looking at your non-metal oxide. So examples of non-metal oxide can be your CO2, SO2 or SO3, or even your NO2. So based on the options that is given to us, it can be sulfur dioxide, it can also be, other options, it can also be your carbon dioxide. Okay, but in this case, because we want to form a strong acid, it will not be carbon dioxide. Because sulfur dioxide, what will it give us? It will give us sulfuric acid. And if we were to use carbon dioxide, it will give us your carbonic acid instead, which is a weak acid. Okay, which one contains a transition metal? So it will be your copper 2 oxide, correct? As well as zinc oxide. So let's take a look at A2. Calcium chloride is an ionic compound. So you want to draw the dot and cross diagram of calcium chloride. So calcium chloride, what is the electronic configuration for calcium? It is 2,8,8,2. But for chlorine, it is 2,8,7. So what does it mean? It means that in order to achieve the noble gas configuration, 2 of its valence electrons from calcium will be transferred over to chlorine, correct? But because I have 2 valence electrons from calcium, how many chlorine will there be? There will be 2 chlorine ions, because each of the chlorine atom can only gain 1 electron to achieve the noble gas configuration. So how will it look like here? Okay, we are only required to show the outer shell electrons, so it means that we are looking at this shell here as well as this shell. Okay, so let's draw for calcium. So how many electrons will there be? Total of 8. Now what charge does calcium have? It will be Ca2+, because it has given away 2 of its valence electrons. So how about for chlorine? Okay, chlorine originally has 7 valence electrons, correct? But in this case, what happened? It has gained 1 electron from calcium, so one of it will be a cross. So therefore, what's the charge of chlorine ion? It will be negative. And remember, how many chlorine ion will we have here? We will have 2. Okay, so this is the answer for, this is the dot and cross diagram for calcium chloride, which is CaCl2. Okay, now let's take a look at part B for this question. So when molten calcium chloride is electrolyzed, okay? So when we're talking about molten calcium chloride, what are the ions present inside? We have Ca2+, which is molten state, so it is in liquid state, as well as chlorine ion, which is also in liquid state. Okay, so we want to write the half equation at the negative electrode. So when we think about electrolysis, the negative electrode, we are referring to the cathode. Okay, so what ions are attracted to the cathode? We are talking about the cations. So between Ca2+ as well as Cl-, your cations will be your Ca2+. So what happens at the cathode here? Cathode, we have reduction taking place, correct? So with reduction, it means there is a gain of electrons. So Ca2+ in liquid state, it will gain electrons to form your calcium, okay, which is also in liquid state. Now, reaction at the positive electrode. So positive electrode, we are talking about the anode, and the anode will attract the N ions. Okay, so remember, at the anode, it is oxidation that is taking place. So oxidation, we are talking about the loss of electrons. Okay, so what happens? Cl minus, which is in liquid, because it is an N ion, it will lose electrons to form your chlorine gas. So now, let's take a look at part C. Predict the products of electrolysis of concentrated aqueous calcium chloride. So, concentrated, always remember, we are talking about your halide ions. Okay, aqueous means there is a presence of water. So, what are the ions present inside? Ca2 plus, Cl minus, H plus, as well as OH minus. So, who gets discharged at the cathode? Cl minus or OH minus? Because remember, it is a concentrated solution, so Cl minus will get discharged. So when Cl minus get discharged, what is being produced? Okay, it will give us chlorine gas at the anode here. How about at the cathode? Between Ca2 plus as well as H plus. H plus will be discharged because it is of a lower reactivity. So your H plus, it will gain electron to form hydrogen gas. Okay, so therefore, what do we get at the end? We will get hydrogen gas as well as chlorine gas. Okay, now let's take a look at part D. So explain using your structure, your knowledge on structure and bonding. Why does calcium chloride has a high melting point? So whenever we are doing this kind of question, we must think about SAEC. Okay, so the very first point, S refers to structure. So what is the structure for calcium chloride? So calcium chloride, it is made out of a metal and a non-metal. So it is an ionic compound. So what kind of structure the ionic compound has? Okay, which has a giant lattice structure. Okay, so it has a giant lattice structure. What does it consist of? This giant lattice structure consists of your Ca2 plus and Cl minus ions. Okay, so what about the attraction here? So due to what kind of attraction is between your Ca2 plus and Cl minus? It is the strong electrostatic forces of attraction. Between what? Between your oppositely charged ions, which are your Ca2 plus and Cl minus ions. Okay, so we talked about the attraction already. So due to the strong electrostatic forces of attraction between your Ca2 plus and Cl minus ions, what does that mean? We talk about E refers to energy. So a large amount of energy is required. Okay, is required to overcome the strong forces of attraction. Okay, so C refers to conclusion. Therefore, calcium chloride has a high melting point. So whenever you encounter this kind of question on bonding, it is important for us to remember SAEC, where S refers to the structure, A refers to the attraction, E refers to your energy, and C is the conclusion. Now, let's take a look at question A3. So copper reacts with concentrated nitric acid. Okay, so what is being formed here? This is your copper 2 nitrate, nitrogen dioxide, as well as water. So what is the name of the salt here? It is your copper 2 nitrate. Why is it copper 2 nitrate? Because of this formula here. Where does this 2 comes from? It means that it is Cu2 plus and NO3 minus. Okay, because copper is a transition metal, okay, that is why we will have a 2 bracket 2 here. Okay, so in experiment 1, an excess of copper is added to our nitric acid. Okay, so calculate the volume of nitrogen dioxide that is being formed. Now, with the concentration here and the volume, what can we first find? Okay, we can find the number of moles of nitric acid. So how do we find the number of moles for nitric acid? Okay, 16 mole per dm cube, okay, of HNO3 is equals to what? Mole over volume. So what is the volume? The volume that is given to us is 0.025. Please convert it into dm cube. Okay, remember 1 dm cube is equals to 1000 cubic centimeter. So the mole of HNO3 is equals to 16 times 0.025, which will give me 0.4 mole. Okay, so what happens after this? We have the number of moles for nitric acid, correct? Then the next thing we can look is the mole ratio. Mole ratio between your nitric acid is to nitrogen dioxide, which is 4:2. So if I have 0.4 moles of nitric acid, I will have 0.2 moles of nitrogen dioxide. And in order for us to find the volume, remember the triangle. Volume is equals to mole over 24 dm cube. So the volume of nitrogen dioxide will be equals to 0.2 times 24 dm cube, which will give us 4.8 dm cube here. Okay, so this will be your final answer. Now let's take a look at this part, okay, the second part for question A3 part B. So a further experiment, okay, experiment 2 was carried out here. Okay, so now let's take a look at the graph given to us for experiment 1 as well as for experiment 2. So now take note, for experiment 1, the acid that we were using was, for nitric acid, it is 16.0 moles per dm cube. Okay, so now we want to find the concentration and the volume of nitric acid that is being used, okay, for experiment 2. So the first thing, we'll take a look at concentration. So what do you realize the initial rate of reaction? For the initial rate of reaction for experiment 2, it is much lower, right? It is much lower as compared to experiment 1. So what does this tell us about the concentration? It means that the concentration of nitric acid will be lower. Okay, so it will be 8.0 moles per dm cube. Okay, so now the next thing we need to find, what is the volume of nitric acid that is being used here? So take note now, for moles per dm cube, the calculation, it is mole over volume. Okay, so take note of this question. What do you realize about the volume of nitrogen dioxide that is being formed? It is half, right? So if you realize for the first part, okay, this one, the volume of nitrogen dioxide that is being formed is 4.8 dm cube. So for experiment 2, it's almost half. Okay, so this one can be about 2.4 dm cube. Okay, so with that, what can we do here? So take note now. So the volume of NO2, okay, in experiment 2 here, it is 2.4 dm cube. So how many moles is this? Okay, so in order to calculate the number of moles of NO2, we take 2.4 times 2.4 divided by 24, which should give us, okay, 0.1 moles. So what do we do after that? Remember your mole calculation, your mole ratio. In this case, we are looking at the mole ratio between nitric acid as compared to nitrogen dioxide, which is 4:2. Okay, so if I have 0.1 moles of nitrogen dioxide, I will have 0.2 moles of nitric acid, correct? So this will give us the number of moles for nitric acid when there is only 2.4 dm cube of nitrogen dioxide that is being formed here. Okay, so how do we find the volume? The volume of nitric acid will be equals to 0.2 over 8 here. So we should get a number, an answer, which is 0.025 dm cube. So the volume of nitric acid that is being used is 0.025 dm cube. Okay, now let's take a look at part C. So we have a sample of copper 2 nitrate. Okay, so the student added aqueous ammonia. So what do you remember about aqueous ammonia? It is used to test for the presence of cations. So what cations are we identifying? We are identifying your Cu2+ in copper 2 nitrate. Okay, so describe what is being observed. So with dropwise, we see a light blue precipitate that is being formed, which dissolve in excess aqueous ammonia, which will give us a dark blue solution. Okay, so the student repeats the experiment, but adds, in this case, they add aqueous sodium hydroxide. Now, aqueous sodium hydroxide is used to also test for the presence of cations, which is your Cu2+, in this case. But what difference will you observe? Okay, take note now, with dropwise, a blue precipitate is formed, but this blue precipitate, which is your CuOH2, in excess, okay, it remains insoluble in excess aqueous sodium hydroxide. So, with aqueous ammonia, you will notice that in excess, the blue precipitate will dissolve to give us a dark blue solution, but with aqueous sodium hydroxide, the blue precipitate remains insoluble in excess sodium hydroxide. Now, let's take a look at question A4. So, we have photosynthesis here. So, we are supposed to draw the energy profile diagram. And they're already given to us that photosynthesis, it is an endothermic reaction. So, when we are thinking about endothermic reaction, it means that our enthalpy change, it is positive. Okay, so to get a positive value, it means that the energy, the total energy level of your reactants will be less than the energy level of your product. Okay, so how will it look like? So this will be the shape for endothermic reaction. But besides that, what should we include? We also need to include the reactants. So what are the reactants here? Your carbon dioxide as well as water, and the products, it will be glucose plus oxygen. Okay, we also need to include the activation energy. So where is the activation energy? So take note, this will be your activation energy. Okay, take note that the arrow is pointing upwards because activation energy is always a positive value. Okay, and the enthalpy change. So the enthalpy change is just the difference between the difference in total energy content, right, between your products and your reactant. So because enthalpy change is positive, the arrow has to be pointing upwards, and this will be our enthalpy change. Okay, we have already included the reactants and products, so this should be the energy profile diagram that you should have here. Okay, now next question, part B. Explain why the rate of photosynthesis increases, okay, when the temperature increases. This question we are referring to the rate of reaction, or it is the speed of reaction. So when temperature increases, what do you notice about the reactant particles? The reactant particles will gain kinetic energy. Since they gain kinetic energy, they will start to move faster. Now, besides that, more of the reactants will possess an energy equal to or greater than the activation energy that is required for the reaction to take place. Therefore, now we'll link to our collision theory, right? So therefore, this increases the frequency of effective collision, thus increasing the rate of reaction. Okay, so where does the 1 mark go to? 1 mark here, 1 mark, as well as the last 1 mark. Okay? Okay, now let's take a look at question A5. So we have Haber process here, okay, which is used to manufacture ammonia. So if you remember the chemical equation, N2 gas plus H2. Okay, remember Haber process is a reversible reaction, so we get your ammonia gas. Okay, so to balance the equation, this will be it. So let's take a look here. Okay, so describe how the percentage of ammonia present at equilibrium changes with temperature and pressure. So let's take a look at temperature. What happens? What do you notice when the temperature increases? When the temperature increases, we notice that the ammonia that is produced will decrease, correct? But what happens about the pressure? When the pressure increases, the percentage of ammonia will also increase. Okay, so with that, let's take a look. The percentage of ammonia increases, okay, as the temperature decreases. Let's take a look. From 500 all the way to 100 degrees Celsius, we notice that as the temperature decreases, the percentage of ammonia increases, correct? How about for the pressure, okay, as the pressure increases, we also notice that the percentage of ammonia increases as well. Okay, now let's take a look at B part. 1. So state the temperature and pressure based on the information that is given to us that will produce the highest percentage of ammonia. So based on this, where is the highest percentage of ammonia? It is 99.9%. So at 99.9%, what is the pressure? The pressure is at 1000 atm. And what is the temperature? It is at 100 degrees Celsius. Okay, so this should be the two values that you have written down here. Okay, so part 2. Explain why the conditions stated in B, part 1 are not used commercially. If you remember in your textbook, right, what is the exact temperature and pressure for Haber process? The temperature, it is 450 degrees Celsius as well as 250 atm. Okay, why don't we use 1000 atm? Because at a high pressure, okay, it is a very expensive process. Why? Because strong pipes and pumps are required in order for us to create a very high pressure of 1000 atm. So we will not want to have a very expensive procedure here. So that is why we leave it to 250 atm. Now, how about temperature? Okay, the ideal temperature, it is 450 degrees Celsius. But based on this graph here, based on the table above, it shows us that it is 100 degrees Celsius. Now, at such a low temperature, okay, at such a low temperature, it will actually cause the reaction to take place at a very slow rate. So that is why we will want to increase the temperature to 450 degrees Celsius instead. Okay, any temperature above 450 degrees Celsius, it is too high a temperature. Instead of producing our ammonia gas, it will result in a backwards reaction where it results in a decomposition of our ammonia into nitrogen as well as hydrogen. Okay, now let's take a look at A6. Proteins are natural polymers, okay, undergoes hydrolysis here. So what is hydrolysis? It is a breaking down of protein into its constituent monomers, okay. So we want to break down this large protein molecule into smaller monomers, which are our amino acids. Okay, so we have a protein molecule here. So the first statement, first question, part 1. Explain what is a polymer. Okay, so polymer, it is a macromolecule. Okay, so it is formed by the joining of many small monomers. Okay, so this large polymer here is made up of many small monomers that are covalently bonded together. Now let's take a look at part 2. We are supposed to draw the structural formula of the 3 amino acids that is present in the polymer. Okay, so what do you notice about the polymer here? What kind of linkage do they have? This is known as your amide linkage. Remember, you all learned 2 kinds of linkage, ester linkage as well as your amide linkage. Okay, so in your amide linkage, what are the functional groups that are present? It is your carboxyl group as well as your amine group. Okay, so in order for us to identify the 3 amino acids, okay, you take note that there are 3 different groups here. Okay, so the first amino acid will be this. Okay, the second amino acid will have to be this part, and the last amino acid, it will be this here. Okay, so how do we draw the 3 amino acids? Let's take a look at the first one. So the first amino acid, okay, it will have a NH, right? So this H is bonded to, this N here is nitrogen is bonded to another hydrogen, and the other part is your carboxyl group. Okay, so this should be the first amino acid that you get. Now what about the second one? Okay, so it will be this middle part here, correct? And this C here is bonded to a amine group again. Okay, as well as your carboxyl group. And the very last part. Okay, so where is this bonded? This is bonded to also your amine group as well as carboxyl group. Okay, so these should be the 3 amino acids that you have gotten from the hydrolysis of this protein. So, suggest a method to separate. We want to separate and identify the 3 components. Okay, so if we want to identify the components, the only method that we can use, it is through chromatography. Okay, so how do we carry out So chlorine in the next part B. Chlorine is used in the manufacture of chloroethene. Okay, so chloroethene has a similar structure to ethene. Okay, so what is the formula for ethene, if you remember? Is C2H4, correct? So remember, ethene, how does it look like? This is a unsaturated hydrocarbon, means there is a presence of a CC double bond, which will look something like this, correct? Okay, so when chloroethene undergoes addition polymerization, polymer N is formed. So how do we draw polymer N here? We want 3 repeating units. Now, let's take a look at how do we draw ethene first. Okay, although this question don't need us to draw ethene, let's take a look. So, what happens when ethene here undergoes polymerization? Take note, the double bond will be broken, okay, into a single bond. So, it means that I will have 3 ethene that are formed here. Okay, so this will be known as your polyethene. Okay, let's check. Are there 3 repeating groups? This is 1 repeating, 2 repeating, and 3 repeating. Okay, so now let's take a look at how to draw our chloroethene. Okay, so chloroethene, this is the formula. So how should it look like? There should be a presence of a CC double bond, correct? And we have 2 hydrogen, 1 H, and a Cl. So check whether this structural formula is the same as your chemical formula. Okay, so remember, because this is addition polymerization, it means that the CC double bond is being broken. So what happens to the double bond? It becomes a single bond, correct? So we'll just copy the rest of the atoms down. Okay, so because we want 3 repeating units, okay, the rest of it will just be the same as the first one. So this will be your polymer N. Okay, so let's check if there is 3 repeating units. The first repeating unit, okay, the second repeating unit, and the third repeating unit. Please check that all the repeating units, they have the same structural formula. Now, let's take a look at C. State one difference between the polymerization process for your proteins as compared to polymer N. Now, take note for addition polymerization, okay, it is a breaking down of the breaking of your CC double bonds, right? So, in the process of breaking your CC double bonds, are there any atoms that is being lost, or are there any molecules that are being lost? No, okay. How about for protein synthesis here? Okay, when we want to form a large protein molecule, this is known as your condensation, correct? Condensation polymerization. So in the process of condensation polymerization, okay, remember, small water molecules will be produced here. Okay, in order for us to connect the amino acids all together. Okay, so let's take a look at the answer. In the manufacture of proteins, remember, different monomers are joined together through what process? This is your condensation polymerization. So with condensation polymerization, always remember that small water molecules will be formed. Elimination of your water molecules. As compared to polymer N has our CC double bond. So this one we are talking about addition polymerization. So with addition polymerization, we are only breaking the CC double bond. Okay, there is no small molecules of water or any other things that are being lost in the process here. Okay. Now let's take a look at question A7. So we have an acid here. Effervescence is observed when lithium is added to malic acid. So describe a test to identify the gas evolved and write the salt form. So now, when we talk about acid, okay, lithium here is a metal. So, when metal reacts with acid, do you remember what is being formed? You will form your salt plus hydrogen gas, correct? So, in your malic acid, where is the functional group? The functional groups belong to your carboxyl group. Okay, COOH here, this is the functional group. So, what gas is being formed? It is your hydrogen gas. So how do we test for the presence of hydrogen gas? we always use a lighted splint. So what happens to the lighted splint? The lighted splint will extinguish with a pop sound in the presence of hydrogen gas. So what is the salt that is formed at the end? Because remember in our acids, okay, what happens to our functional group? It is your COOH, right? So what happens to the H here? The H will get dissociated, correct? So your H will be eliminated and lithium will be attached to your H part. Okay, we'll replace the H. So you will notice that Li, there will not be a H. Okay, LiO2, then this part C, which is this one, CH2, which is referring to this, okay, CH, this part here, okay, this C is bonded to an OH and we have COOLI, okay. Okay, let's take a look at part B. An alkene F reacts with steam to produce the following alcohol group. Okay, so alcohol group, remember we always have your hydroxyl group. So alkene means there's a presence of CC double bond here. So we want to find out the structural formula of F. So where is the CC double bond? Okay, remember when steam is being added, correct? This is known as your hydration process. Okay, this is hydration. So the steam will be added to the CC double bond, correct? And it will break the CC double bond, correct? To give you your OH as well as your H here. So what happens between this part? So it means that, okay, where will your CC double bond be? It will be between these two. So there will be a double bond here as well as this part because we have OH and a H. Okay. So this will be how your structural formula for F will look like. Now, to take note, okay, if you are not sure whether or not it is correct, count each of your carbon atom. Make sure that there's a maximum of only 4 covalent bonds that is present for each of the carbon atoms. Okay, so remember, we are talking about hydration. So what are the conditions for hydration? We have phosphoric acid, H3PO4, okay, takes place at 300 degrees Celsius and 60 atm. Now let's take a look at question A8. So for question A8 here, okay, we have silicon is in a group 4 element, correct? So what does the equation want us, what does the question want us to do? We want to find out, show the relative atomic mass. So we are talking about the AR of this here. So what happens? All this here, so it means that I have 3 isotopes. Okay, so how do we calculate the AR for silicon? So based on all this here, these are the abundance, the percentage abundance of it. Okay, so how do we calculate the relative atomic mass of silicon? So the first one, okay, we have 92.21 over 100%. What is the AR for the first isotope? It is 28. Okay, so I plus, what is the other percentage? 4.7 over 100 times 29, which is the AR for the other 4.7% of the other isotope plus 3.09 over 100 times 30. Okay, so if you calculate everything together, it will give us 28.1. So this is how we show the formula, show the working of how we concluded to get the AR of silicon, which is 28.1. So write a balanced chemical equation for the extraction of silicon from sand. So how do we write it? Okay, let's take a look here. Okay, so it can be, silicon can be extracted by heating sand with carbon. Okay, the product form, one of the product is silicon, the other product is your carbon monoxide. So what is the formula for sand? Sand is your silicon dioxide. Okay, so how do we write it? So SiO2 plus carbon to give us silicon plus carbon monoxide. So for this, I need to balance the chemical equation. So this will be how it looks like here. Okay. Okay, now let's take a look at part C. A student made this following statement about silicon dioxide. So silicon dioxide can be used as an electrode in electrolysis as it has the same structure as graphite. Now, let's take a look. What are the two errors in the statement here? The very first thing, silicon dioxide, okay, it cannot be used as an electrode. Why is that so? Okay, if you remember the structure for silicon dioxide, each of the silicon atom, okay, is bonded to 4 other oxygen, and each oxygen is bonded to 2 silicon. Okay, so you notice that for silicon atom, it already has an octet structure already, as well as for oxygen. Oxygen also has an octet structure, so it does not have any free moving electrons here. It does not have any delocalized mobile electrons to carry charges. Okay, therefore it cannot conduct electricity. Okay, so in order for it to be an electrode, it needs to have mobile charge carriers in terms of electrons here in order to allow electricity to be conducted. Now, the next thing, okay, the next error is that silicon dioxide and graphite, they do not have the same structure. They do not have the same structure. Why is that so? Now, let's take a look at the structure for silicon dioxide that we have drawn earlier. This structure is your tetrahedral arrangement. Okay, but how about graphite? For graphite, okay, take note, one carbon atom is only bonded to 3 other carbon atoms. So, what kind of structure is this? This is known as your hexagonal plane arrangement. Okay, so it means that both of them, they do not have the same structure. So let's take a look. Each carbon atom is bonded to 4 oxygen atoms, while each oxygen atom is only bonded to 2 silicon atoms. So this will form a tetrahedral structure. But for graphite, which is made up of carbon, each of the carbon atom is only bonded to 3 other carbon atoms, and the structure that is formed is a hexagonal plane arrangement. Okay, so that is why silicon dioxide and graphite, they do not have the same structure.